Okay, so for part A, there's an f of g force that always exists on the block. And we also see that there's an F force being applied. And if we drew the components to this F force, we would see that there's an Fy and an Fx. These are components, so we don't draw them. But since we know that the block is moving on the floor, we also know that all the downward forces, so Fg and Fy, must equal to the upward force, so Fn. We also see that there's friction here, so we can just add an F of k. For part B, it asks us to find the slope. So we know that the slope, which we'll be taking as A, is the change in y and the change in x. So this will be our vertical axis. And this will be our horizontal. Now how do we solve for A using these variables x and t? Well, we know the displacement formula, which is delta x, but we can just put x instead because that's what the problem gives to us. X equals to 1/2 of A times t, but since we're given delta t, we can just write that. And then plus VI t. Now here we're told the box of mass m is initially at rest. So VI is equal to 0. So this whole thing is equal to 0. And we can just take this equation. Now we want to solve for A. So let's just, I'm actually just going to write it down here because there's more space. X equals 1/2 A delta t. I'm going to just try to isolate for A. So I'm going to multiply this 2 up and then divide this to the bottom. So 2x over delta t squared equals 2a. And we see here with this formula that whatever the numerator is our vertical axis, and whatever our denominator is our horizontal axis. So we can just go ahead and write that. And then our units in meters. And our units seconds. I'm just cleaning up my work. We're asked to record any quantities, so I'm just going to plug this equation into here using these values. So what I mean by that is this becomes 2x in terms of meters, and I'm going to multiply this by 2 to get 0.072. And I'm just going to do that for the rest of the values. So this becomes 0.468. This becomes 0.986. This multiplied by 2 is 1.458. And this multiplied by 2 is 3.042. Okay, and then now we can move on to the horizontal axis here. So plug that in. Delta t squared in seconds. And I'm just going to put this in parentheses. So this squared is 0.04. This squared is 0.2601. This squared is 0.5476. This squared is 0.81. And this squared is 1.6. We're asked to plot for the quantities, so I'm going to put, since we decided that the horizontal axis would be delta t squared, I'm going to label it as that in seconds. And then the vertical axis is 2x in meters. Okay, and then for my units, I'm going to put this as 0. This is 0.62. So what I was doing here was I took the largest value and divided it by 5 to see how big of an interval I wanted, and it was 0.62. Here I took the largest t value, which was 1.69, rounded up to 1.7, divided by 5, and then each interval I just had 0.34. Okay, so now it's time to plot the points. And then I drew a line that best fit all the points. It's kind of squiggly, but yeah. Okay, so an experimental value for acceleration. I'm just going to use this slope. This looks like a solid point here, here. And then this looks like it's going through 0, 0. So I'm just going to guesstimate that is about 1.488. And this is about 0.816. So if we put 1.488 minus 0 over 0.816 minus 0, we'll get about 1.8235. So I'd say that my experimental acceleration is about 1.8235 meters per second squared. Okay, so I wanted to also use the best fit line because that would probably give us a more accurate acceleration and line on the graph than what I was just eyeballing. So if I plug in the points in my calculator. Okay, so here's what my calculator looks like. This is all my 2x values in list 1, so that means this has to be my vertical list. And list 2 has all my delta t squared values. So this will have to go on my horizontal. So to find the best fit line, I go into stat, calc, and then linear regression. With the horizontal list as the one with all my t values, t squared, 2x. And then a, the slope I get is 1.8. So according to the best fit line, acceleration is about plus 1.8 meters per second squared, which is pretty close in value with my original guess. We know that net force equals ma, and since it's not moving up or down this y-axis, we know it's going to be moving along this x-axis. So let's just take the net force in the x direction equals to the mass times acceleration in the x direction. And the reason we can replace a with ax is because there's no ay, so a and ax are just the same. Now we know that there are only two forces acting on the block horizontally, which is this component, Fx, and this force, Fk. So net force in the x direction equals Fx minus Fk. And we can just set these as equal to each other. Now we can expand f of x using the trig function cosine, because that's equal to adjacent over hypotenuse, and the adjacent side is fx, and then the hypotenuse is f. Since we want to solve for fx, we're just going to multiply this up to isolate. So f cosine theta is equal to fx. And then we're going to substitute it into there. And then we want to derive an equation for mu k for kinetic friction. However, we don't have that. It's part of this fk. So we're going to expand that. And we know from this equation of mu k, it is equal to fk over fm. If we multiply this up, we can isolate for fk, which is just fn times mu k. And then we want to expand this fn. We know that the net force in the y direction has to be equal to 0 because the acceleration in the y direction is 0. So in the y direction, we have 3 forces, this Fy component, an Fg, and then an Fn. So Fy equals to Fn minus, or the net force of Fy equals to Fn minus Fy minus Fg. And then we can just set that equal to 0, and then add these two terms over to isolate for Fn. So let's just continue working down here. So we can plug it in to this equation. And then we can expand for Fy and Fg. Again, by using the diagram. So sine theta equals opposite over hypotenuse, which is also just this Fy component, which is opposite to the angle, over hypotenuse F. And then to isolate for Fy, we multiply this up. Fy. We can plug that in there. And then we know Fg will just be equal to mg. So let's rewrite it. Okay. So we have this statement. And then we're going to plug that in to there. Okay. And then our goal here is to isolate for mu k. So I'm going to add this to the other side because I want it to be positive. And then just subtract this max to the other side. I'm going to make some room for myself. And then we aren't given max, even though we know that ax is just equal to a. So let's just replace it with a. Just because we want to stay true to the variables that were given. And then divide both sides by f sine theta plus mg so that those two can cancel out. And then you get your final equation for mu k, which is f cosine theta minus ma over f sine theta plus mg. Okay. So part F asks us to find the kinetic frictional force. So we know that the net force in the x direction is what is going to include the frictional force because it is horizontal. So again, we have this component Fx and then this force Fk. So Fx, the force going right, minus Fk, the force going left. We also know that net force is equal to ma. So we can set these as equal to each other. And then we can add this to the other side and subtract this to the other side so that we can solve for Fk. Again, we can expand this to be f cosine of theta. And then we can just get rid of this x because we know that a in the x direction is the same as just a. And then we plug in the variables that we are given. Remember that we solved for a in one of our previous questions, so we can go ahead and plug these variables into this equation. And when you plug it into a calculator, you're going to get that Fk is equal to 2.4. Let's just do a negative because it's going against the line of motion. So for part G, we know that the equation for mu k is Fk over Fn. And we can just expand this. We know that Fk is just negative 2.4. And then Fn we solved for earlier as well, which is mg plus f sine of theta. So we're given these variables, m equals 2, f equals 12, and theta equals 60. So we just plug those into there to solve for mu. And then we should get negative 0.08. But I'm just going to take the magnitude because it's just a coefficient and it doesn't need direction. Okay, so for part H, I'm arguing that when the angle of the applied force is decreased, it will increase the acceleration of the block. Now let's solve for acceleration of the block. Again, like I said, the acceleration in the y direction is 0 because it doesn't move up or down off the surface. So the net force is just m times a. And then we're trying to solve for this. So what other forces exist in the x direction? Well, it's just fx minus fk, which again we can expand. And then we can set these as equal to each other because they're both the net force in the x direction. Okay, and then we're trying to solve for a, so we divide both sides by m so these can cancel out. Okay, so our final equation for a is this. Okay, so we're asked what happens when theta decreases. And when theta decreases, cosine increases in value and sine will decrease in value. Now this is significant because if this number is becoming larger and this number, which is being subtracted, becomes smaller, a bigger number subtracting a smaller number is going to result in a bigger number rather than a smaller number subtracting a bigger number. So that means that when theta decreases, if this numerator is overall becoming bigger, then acceleration will overall become bigger. So we're gonna go ahead and label this as the A, and the units would be meters per second squared for the y-axis, and then the x-axis would be t in units of second. So we're asked to use the time interval that they give us. So I'm just going to go ahead and label it. They start with 0, and then 0 0.2, 0 0.51, 0 0.74, 0 0.9, and then 1.3. So we know the entire time that acceleration is just 1.8. And the easiest way I can chunk this up is by 0.5s on the y-axis. And then the acceleration is 1.8, so it would fall somewhere right here. And that's our graph, our acceleration versus time graph. And then for the velocity graph, I'm going to label this side as v. The units would be meters per second. And then again, the x-axis in time in seconds. So we're using the same time interval. And I'm just going to use the same chunks as I did for the acceleration graph. And since acceleration is just a straight line, that means that v is increasing at a constant rate. So I'm just going to do like a straight line this way. And this is my velocity versus time graph. Okay, and then lastly for the position versus time graph, we're going to label this x in units of meters, and then this axis is time in units of seconds. So same time interval. And then with the x values that were given in the graph already, The highest value is 1.521, so I'm just gonna do 1.6 divided by 5. So I'm gonna do intervals of 0.32. Okay. And then we're asked to plot all the points. So I'm just gonna write them out here just to make it easier for me. So at time 0.2, it's at 0.036. So super low, somewhere down here. Times 0.51, that's 0.234. So still below this, maybe here. 0.493, maybe like here, a little closer to the bottom. Actually, and then 0.229, oh, that's a 7. 0.729. And then 1.521, which is super close to this. And then I'm just gonna connect all the dots. Assuming that the initial position is 0, I'm just gonna graph that for time equals 0 at the start. And then connect these dots. And that's my position versus time graph.